Good day everyone and welcome to Lesson 6. We are now on the study of recycle, bypass, and purge. This is a continuation of our discussion for material balances in multiple units because one of the prerequisites of having a recycle, bypass, and purge is that you are considering multiple units. Okay? Let's begin by analyzing or by learning how to represent recycle, bypass, and purge in diagrams. First, recycle. In simple words, we can explain recycle as you are taking a little part of a certain stream and sending that part back upstream. This serves several purposes, one of which is it's normally used to improve recovery. Let's say, for example, you are doing a process wherein you are recovering something via extraction or via distillation, and the percent recovered is not that high. What you can do there is you can perform recycle so that you can send back a part of your products back to your inputs so that it will be processed again and again. That applies to processes without chemical reactions. But for processes with chemical reactions, we do often see recycled processes as well because some reactions are thermodynamically limited. As such, you will not get a very high conversion on a single pass alone. That's why we have to recycle the products back. So how do we draw a diagram for recycle? Okay. So imagine that we have a unit here. Let's call this our unit. So whatever unit this is, we have a feed coming into the unit. We also have a product coming out of the unit. The recycle in this case would be coming from part of the product and it will join the feed. So we take part of the product and we recycle that back to the feed. This is then our recycle stream R. You will see here that we have created 2 points of intersection. This is the first point of intersection. This is the second point of intersection. And they are very different. The first one, we call this a splitting point. It's called a splitting point because simply your stream here, let's call this stream B. Stream B is the stream that directly goes out of the units. And then you divide stream B into 2 streams, that's stream P and stream R. This is called a splitting point because its primary purpose is to just split the stream or just divide the stream, not necessarily into equal portions. You just have to separate your recycle stream from your product stream. Now, some key things to remember about the splitting point is that whatever you do on the splitting point, the composition stays the same, or the composition stays constant if you are on the splitting point. Therefore, whenever you see a splitting point, all of the streams that are connected to the splitting point must have the same concentration or must have the same composition. Example, if I say that my product contains 20% water, just for example, this also means that my recycle also contains 20% water, and my stream B, which is the output of the unit, should also contain 20% water. Because remember, you're not doing any separation or you're not doing any fancy process. You are simply just dividing the stream. Therefore, they should have the same composition. But they will not have the same flow rates or they will not have the same masses. Okay? In the splitting point, you can also perform an OMB. So therefore, if we are talking of multiple units, you can set your boundary at the splitting point only. Okay? You can treat the splitting point as a separate unit. So let's say, for example, we treat the splitting point as a separate unit. So at the splitting point, we can say that the OMB in this case would be B is equal to R plus P. So it's the same material balance that you are used to do, just that we are using this now in a splitting point. Okay? Now the other point here at the end of the recycle stream is called a mixing point. It's called the mixing point because it is at this point wherein we are mixing the recycle stream with the F. Okay? In this case, for the case of recycle, this F is now called the fresh feed, because we now have two types of feed. The first one is the fresh feed. The second is the stream that goes directly into the units. We call that M. And M here is called mixed feed. Okay? Do not confuse fresh feed with mixed feed. They would have different compositions. So unlike the splitting point, whenever you see a mixing point, you treat this as a mixer. Okay? We treat that as a mixer because, again, you are simply mixing R with F to get the mixed feed. The compositions are not constant. And therefore, for you to be able to know the compositions of the mixed feed or the recycle stream or the feed, you must perform material balance on the mixer itself or on the mixing point itself. We can have another balance here at the mixing point. Your OMB would be, your inputs are feed and recycle, and your output is the mixed feed. Okay? If you take a look at the material balance of the splitting point and the mixing point, they are very different. In the splitting point, normally, you no longer need to perform component balances because compositions are constant. If you do need to perform component balances at the splitting point, that is just to solve for the other values of the streams. No? For the mixing point, you have to perform the component balances because that is one way for us to determine the compositions of the mixed feed. No? So you can perform your component balance at the mixing point. Now, in terms of what boundaries can we set for a recycle problem? So let me first erase some things. So do not forget how to draw a recycle diagram. Also, do not forget the functions of the splitting points and the mixing points. Okay, how do we set boundaries for these types of problems? We have the first type of boundary, the overall boundary. Let's denote this with red. The overall boundary in this case will not be including the recycle stream. So if I draw my overall boundary, you see here that the only stream coming in is F and the only stream coming out is P. Therefore, if you write your OMB for the overall boundary, it's simply just F is equal to P. The R or the recycle stream will not appear on your overall boundary. If you want the recycle stream to appear on your OMB, then you can perform the OMB on the mixing point, on the splitting point, or you could perform another boundary at the unit itself. So let me demonstrate. Let's use green. So if we use a unit boundary, you will only be writing your boundary at the direct vicinity of the unit. So this is what it looks like. Therefore, if you write your OMB for the units only or for your unit boundary, what should it look like? It should only look like M is equal to B, because the mixed feed is the one that's immediately going into the unit and stream B is the one immediately going out of the unit. So for unit boundary, our OMB is very different from our overall boundary. So you might be asking, where is the recycle stream in this? Well, the recycle stream on your unit boundary would also come from the OMB from the mixing point and the splitting point. To recall, at the mixing point, our OMB is F plus R equals M, and at the splitting point, our OMB is B is equal to R plus P. So as you can see, you can substitute both OMBs from the mixing point and the splitting points back to your unit boundary or to your OMB for the unit boundary. So what should that look like? It should look like F plus R equals R plus P. There's your recycle stream. It does appear on the unit boundary. But if we simplify this equation, R cancels, and you are left with F is equal to P, which goes back to your overall boundary. You see here, all of these balances are interconnected. No? In this case, for this simple recycle process, you can perform 4 different sets of balances for 4 boundaries. You have your overall boundary, your unit boundary, your splitting point, and your mixing points. Okay? And those 4 sets of balances would be important when you are trying to find multiple equations to solve at the same time, whenever we have multiple unknowns. Okay? Remember this format of the recycle stream, or of the recycle process. Next. Okay, next we have the bypass. We are now on the second type of unit for this lesson. The bypass is the opposite of the recycle. For the recycle, you are taking a part of the product and recycling that back to the feed. For the bypass, you are taking a little bit of the feed and then you are skipping the units and then transferring that to the product itself. Okay, so let's illustrate that. So we have our unit, we have our feed, and our product. For bypass, we take some of the feed and then you bypass the units, or you skip the units, you join the bypass with the product. Okay, so it's the exact opposite of the recycle process. You can see here that we also have 2 intersections, one over here and the other one in here. So these are also the splitting point and the mixing points, but since this is the opposite of recycle, these are now interchanged. This is now our splitting point, and this is now our mixing point. Okay, the concept of the splitting point and the mixing point are just the same as that of the recycle. So in the splitting point, the compositions are constants between F, B, and let's call this A, and then let's call this G. No? For your mixing point, compositions are not constant because you are mixing G with the bypass stream B. Okay? The same as with the recycle stream, you can also perform 4 different balances here, or 4 different boundaries. You can have the system boundary, or the overall boundary. You can have the unit boundary, the splitting point, and the mixing point. Okay? Always remember that bypass is the opposite of recycle. Next. By the way, why do we need to bypass, or why do some processes need the bypass operation? Bypass operation is normally used in the manufacture of food products that are heat sensitive. Let's say, for example, you are trying to produce concentrated orange juice. In the concentration of fruit juices, normally we are applying heat, or normally the unit process is an evaporator. So you are evaporating some of the water to make the fruit juice more concentrated. Well, one of the consequences of boiling down fruit juice to make it more concentrated is you are losing some of the flavor components, because majority of the flavor components in fruit juices, especially in citrus fruits, are very volatile. No? So as such, when you produce your concentrated juice, its quality is not the same as that of the fresh juice. To solve that problem, we apply a bypass operation on the evaporation of fruit juices. No? So we take a little bit of the feed, which contains the volatile substances that completes the flavor of the orange juice. We bypass the heating process in the evaporation, and we mix the feed, or we mix some of the feed with your concentrated products. So what you have is, you still get a concentrated product, but then you have a concentrated fruit juice that still tastes like orange juice, for example. No? So that is just one of the many applications of bypass in the process. Next. Last one, purge. Okay. So the purge is normally associated with the recycle, or it's normally in tandem with the recycle. If you take a look at this diagram, you can see a recycle stream, but there is another stream attached to that recycle stream. So let's try to draw an example of a purging process. We still have our units. We have our inputs feed, and we have our outputs product. So as I've said earlier, purge is normally associated in tandem with recycle. So let's draw a recycle stream. This is a typical recycle unit. No? You have the splitting point here, and you have the mixing point here. But what separates purge from a normal recycle is that we have another offshoot process here. We will call that G. This is your purge stream. You see here that we have introduced another intersection. This is this part, the intersection between the recycle stream and the purge stream. What is that stream, or what type of point that is? Is it a mixing point or a splitting point? So it's quite obvious that this is another splitting point. Let's first label some of the streams. We call this the mixed feed. And then let's just call this A, and let's call this B. No? So you see here that stream A is the direct output of your units. It's being split into P and B, while B is further split into the recycle stream and G, or the purge stream. Okay? So this is an example of a purge stream. It's almost always connected to the recycle stream. Why do we need to, or what's the main purpose of a purge stream, or why do we need to use a purge stream in processes? So normally purge streams are used in reactive processes wherein there is a chemical reaction involved and there is an inerts in your feed. So if you don't have a purge stream, what could happen is that your inert substance could build up in your system. Because remember, if you run a full recycle, if you are not recovering your inerts as one of your product, the tendency would be the inert would just keep recycling on your entire unit, and it would just keep accumulating. No? So if you go back to your mass balance, there would be an imbalance in the in and in the outs of the inerts. So there would be accumulation. Okay? Whenever you don't want accumulation in your system, you install a purge stream. So normally the purge stream is a waste. It's just a very small value, or it's a relatively small value that we can consider this as a waste of the process. Okay? We will be visiting purge and recycle in some of our examples. No? Bypass is very rarely encountered in material balance problems, but I would still try to give an example of bypass. Let's have our first example. Benzene and toluene are to be separated in a distillation column. The feed is composed of a mixture of the two, with 50% benzene and a total flow of 160 kilograms per hour. The material taken off from the bottoms is found to flow at a total rate of 60 kilograms per hour and contains 50 kilograms per hour toluene. The distillate has a total flow of 100 kilograms per hour and a composition of 0.3 mass fraction of toluene. What is the reflux ratio, or the amount recycled per amount of distillate, if the flow into the condenser is 150 kilograms per hour? So let me first write the given. Here is our diagram. So we have the distillation column. We have the feed, 160 kilograms per hour, 50% benzene and 50% toluene. The bottoms is 60 kilograms per hour, containing 50 kilograms per hour toluene, and the remaining 10 kilograms per hour is benzene. Now, there's something a little bit different from this distillation column. No? We have included a condenser. So by the way, this is normally how most distillation columns work. In our previous lessons, I have been representing distillation columns as simply having the distillate and the bottoms as two of its products. But the distillate normally has to be condensed to its liquid form. So that's why we have included here a condenser. If you take a look at stream A, which is 150 kilograms per hour, that is the stream that directly comes out of the distillation column. It is still in the vapor phase. So it enters the condenser. It is then condensed to a liquid phase. The flow rates of A and B are the same. They just have different phases. And then you see here that stream B is divided into two streams, the distillate or the product, and R or the recycle stream. In this case, we call this a reflux. No? So for distillation operations, we generally call this reflux, wherein a part of your distillate product is sent back to the distillation column. The purpose of that is to enrich or to have a better composition of the distillates. Okay, so this is a recycle stream. So let's take a look at our required. We are required to determine the reflux ratio. The reflux ratio here is the amount recycled per amount of distillates. Reflux ratio. The amount recycled over the amount of distillates. So the amount recycled is R, or that is the stream that is sent back to the distillation column, and the distillate is D. So we are effectively solving for the value of R over D. Looking at our given, we already have a value of D, that is 100 kilograms per hour. So we just have to solve for R in order for us to solve for the reflux ratio. Okay? First, let's set our basis. In this case, we are given mass flow rates, so therefore our basis is 1 hour operation. Now, let's set our boundaries. If we take a look at our diagram, if I set my boundary as the overall boundary, that will not give us anything because your F is already given, your D is already given, and your B is already given, and those are all of the components of your overall material balance. So we will not get anything from the overall material balance. Okay? So in this case, I would like to set my balance to the splitting point. So where's the splitting point? If you take a look at here, this is our splitting point. So why did I set my boundary to the splitting point? That's because I'm looking for the value of R. I have the value of D, and I will have the value of B because B is just the same as A. It's just different phases, no? Let's see. So set the boundary at the splitting point. So what is our OMB? B is equal to R plus D. But we have to take note that A is equal to B because it's just condensed. So therefore, we can say that our OMB is A is equal to R plus D. Substituting the values, we have 150 is equal to R plus 100. Therefore, R is equal to 50 kilograms per hour. Okay? So we now have the value of R. We can solve for the reflux ratio. R over D, so that is 50 over 100. The reflux ratio is 0.5. Significant figures, we need 3. Okay, so this was a relatively easy problem because we did not need, or it did not require us to perform component balances because there's no need for it. We just need to determine the value of R. Okay, in these types of problems, what's important for you to know is you need to know how to spot, or you need to know how to differentiate between a splitting point and a mixing point because that's very important and they have very different properties. It would also be important, or it would also be helpful if you can identify whether this is a recycle, bypass, or purge process. No? So in this case, this is a recycle. Next example. Shown below is a hybrid evaporator crystallizer process to obtain potassium nitrate crystals. The fresh feed contains 20% potassium nitrate. The evaporator product contains 50% potassium nitrate, and the crystal product is 4% water. The mother liquor contains 600 grams potassium nitrate per kilogram of water. Determine the flow rate and composition of the inputs to the evaporator. Let me first write draw the given. Okay, here is our diagram. So this is a combination process between the evaporator and the crystallizer. The purpose of this tandem process is for your feed to be more concentrated before it enters the crystallizer, and that allows us to extract more crystals. No? Let's start with R. So if you take a look at R, we were not given its composition, but we are given a ratio of the components. So it says that there is 600 grams of potassium nitrate per kilogram of water. So that is 600 grams of potassium nitrate per 1,000 grams of water. If we consider first R, if you set your mini basis as 1,000 grams of water, you therefore have 600 grams of potassium nitrate. And we can solve for the mass fraction of potassium nitrate, which will be important later, no? So we can solve the mass fraction as 600 divided by 1,000 plus 600, which is 600 over 1,600, 0.375. 37.5% of the recycled stream is potassium nitrate. Now, you might be wondering, for the crystallizer process, our normal outputs are the crystals or C and the mother liquor. Well, in this case, the mother liquor is the recycle stream because the mother liquor is sent back to be mixed with the fresh feed to give us the mixed feed, which is then fed to the evaporator. If we complete the labels of the process, we should be labeling M, which is the feed to the evaporator. Okay? We are required in this problem to determine the value of M, or the flow rate of the mixed feed, plus its composition. So we start our solution by defining our basis. In this case, we are given the flow rates of the feed, 10,000 kilograms per hour. So a good basis would be 1 hour operation. Next, so just as how we solve multiple units, we first set our first boundary. So where can we set our first boundary? We can set it at the entire system, and let's see if we can get something. If I set my boundary at the entire system, that would exclude the recycle. It will only include the feed, the crystal products, and the evaporated water. So this is our overall boundary. What is your OMB? That would be F is equal to W plus C. We know the value of F. We substitute 10,000 is equal to W plus C. This is our equation 1. Now, to solve for the value of W and C, we have to perform component balances. And there is a tie component, it's potassium nitrate. It only enters at F and exits at C. So let's have the component balance. Potassium nitrate. So what is our balance? 20% of the feed, so 0.2 times 10,000 is equal to, there's no potassium nitrate in W, so it's 0.96 times C. From this equation, we can directly solve for C. 10,000 times 0.2 divided by 0.96. So C is 2083.33 kilograms per hour. I will not yet be applying significant figures, no? So we will just apply significant figures to the final answer, which is M. Okay, so we are done with the overall boundary. So next is we find another boundary that would give us the value of M. You can choose the evaporator. So if you choose the evaporator, you don't know M, you don't know P, but you know W. But you cannot solve that because we are not given the composition of M and we have to determine it. we cannot choose the evaporator. A feasible option would be to choose the mixing point. By the way, here's the mixing point. That is a viable option because the mixing point contains M. It also contains R and F. We already know the value of F. We know the composition of F and R, no? But we don't know the composition of M. So the balance at the mixing point will give us a hanging equation. For that, we first need to get the value of R. Because if you can get the value of R, you simply add that with the value of F and you can get the value of M. And for us to get the value of R, we have to perform our balance at the crystallizer. So take a look at our next boundary. If I set the boundary at the crystallizer, your OMB would include R, which is important, no? So our OMB is P, the input, is equal to the output C and R. We already know the value of C, so we can substitute. This becomes P is equal to 2083.33 plus R. This is our equation 2. Now we have two unknowns, so we need another equation that has P and R, and we can get that from a component balance. So let's use the potassium nitrate balance. This is the reason why earlier we considered stream R and we determined the mass fraction of potassium nitrate in R because we will be using that in this potassium nitrate balance. So what do we have? So we have 50% of P is equal to 96% of C. So 96% of 2083.33 plus 37.5% of R, so 0.375 R. This is our equation 4. We can now solve this should be equation 3. We can now solve simultaneously equations 2 and 3. So solving 2 and 3. What do we have? Okay, so let's have P as X and R as Y. So the constants are 1, -1, and 2083.33. For the second equation, that's 0.5, -0.375, and 0.96 times 2083.33. Okay, this is our P. 9749.98 kilograms per hour. Next is our R. 7666.65 kilograms per hour. Okay, so we now know the value of R. If you go back to the mixing point, it now becomes easier to solve for the value of M. So let's consider the mixing point as our third boundary. So let's now consider your mixing point as our third boundary. What is your OMB at the mixing point? It's simply F plus R equals M. We know the value of F, it's a given. You have already solved for the value of R, so we can directly solve for the value of M. M is simply 10,000 plus 7,666, so we have 17,666.65 kilograms per hour. Using the correct number of significant figures, 4 significant figures. This is 1, 2, 3, 4. 17,670 kilograms per hour. So we now have a flow rate for the mixed feed. So next, how about the composition of the mixed feed? Okay. We know that in the mixed feed, we have two components. We have water and potassium nitrate. So let's write that here. Potassium nitrate and water. So we will be using variables to represent the mass fraction of potassium nitrate and the mass fraction of water. So I will be using X as the mass fraction of potassium nitrate in M. Sorry. Okay. Let's use X as the mass fraction of potassium nitrate in M. And for water, you can represent it as Y, but you would have too many variables. So in order for us to avoid that, the mass fraction of water would now be 1 minus X because it's just a binary mixture. No? So it's X and 1 minus X. So let's perform the potassium nitrate balance on the mixing point for us to determine the mass fraction of potassium nitrate. Potassium nitrate balance. What do we have? In your input, 20% of 10,000 plus in R, 0.375 of R. R is 7666.65. That is equal to the mass fraction of potassium nitrate in M, which is X, multiplied by M, which is 17666.65. We can solve for the value of X. So that's 10,000 times 0.2 plus 0.375 times 7666.65 divided by 17666.65. So the mass fraction of potassium nitrate in the mixed feed is 0.2759. This is for potassium nitrate. And for water, you can simply subtract this from 1. 0.7241. Okay, so we have determined the mass fraction. We have determined the flow rate of the mixed feed. We have also determined its composition. So this is how you approach a recycle problem. No? Sometimes it would be very beneficial for you to start with the overall boundary so that you can solve for other variables first before going to the individual boundaries like the crystallizer, the mixing point, and etc. Okay? In this case, it's okay if you start with the OMB of the mixing points, and then once you realize that you don't have enough given or you don't have enough information, you can proceed with the material balance for other units in the hopes that you would get more information. And then you could always return back to the equations. Okay, next problem. So in this problem, we are given another diagram. To save energy, stack gas from a furnace is used to dry rice. What is the amount of recycled gas in pound moles per 100 pounds of P if the concentration of water in the gas stream entering the dryer is 5.2%? So let me first copy the given. So here we have the diagram for example number 3. We have two types of streams here. No? We have the lower streams and we have the upper streams. So as you can see, the lower streams are the solid ones. No? That is your rice. No? And we are using air, or in this case we are using gas, stack gas, for us to dry the rice. The concept behind this is that the gas absorbs or the gas vaporizes some of the water from the rice in order for the rice to be dried. No? So the lower streams are solid, that's your rice. The upper streams are vapor or gases. That is very important for us to differentiate because water in here exists in two phases. The first one, in the bottom streams, no, water exists in the liquid phase, while water at the top streams exists in the vapor phase. So that's just an important note. Okay, so let's analyze this problem. We are required to determine the amount of the recycled gas in pound moles per 100 pounds of P. Okay? Based on this required, it's quite obvious on what basis would we be using. So in this case, our basis is 100 pounds of P. Another thing to note is that there is a different representation between the bottom streams and the upper streams. In the feed and in the product, the units are in pounds. It's a unit of mass. While for the upper streams, the S, W, and R, they are in pound moles because they are gaseous streams. So that means that we also have two types of representations of composition here. In your F and in your P, those percentage are percentage by mass because it's in the solid state. In the upper streams, in the stack, the W and the R, those are all in percent by mole because we are required to get the amount of recycled gas in pound moles. No? So that is in moles. You have to keep in mind that we are dealing with both mass and moles, and you cannot combine mass and moles in OMBs. I will be illustrating how do we divide that. So first, for you to not be confused with the divide between mass and moles, so let's just draw a line in the middle of the bottom and on the upper stream. So everything on the bottom is in terms of mass, everything at the top is in terms of moles. Okay, so let's start. First, we set our overall basis. Our overall basis is still this. Your inputs are S and F, and your outputs are W and P. Now, overall boundary. What is our OMB? The OMB in this case is F plus S is equal to W plus P. We know the value of P. So this becomes F plus S equals W plus 100. The problem with this OMB is that it has mixed units. Some of these are in pounds, some of these are in pound moles. So S and W are in pound moles, while F and P are in pounds. If you go back to our lesson in dimensional homogeneity, we cannot add pound moles with pounds. So therefore, we cannot operate on the OMB of this overall boundary unless we make some changes to our equations. One thing that we can change is we can treat the bottom streams and the upper streams separately, although we are still talking of the OMB. What do I mean with that? You take a look at the balance of the streams. So for streams F and P, let's say for example for stream F, you have 75% rice and 25% water. So that's another way of saying that is you have 25% of water and the remaining is inert substance, or the remainder is rice. No? The same thing goes with your stream S and stream W. For stream S, it says that you have 4.73% water. So what's the balance of that? 100 minus 4.73. 95.27% of S, we do not know what it is, but we are going to call it inert gas. Okay, so let's first consider S. You have 4.73% water. The remaining 95.27%, we simply call it inert. No? We do not care what it is as long as it does not interfere in the drying process. Because in this problem, we are mainly concerned about water because water is the species that is being transferred from the rice to the gas. Let's also consider stream W. This contains 9.31% water. If you subtract that from 100, we can get the percentage of the inert. 90.69% inert. If you also take a look at stream M, or the stream that goes into the dryer, That's 5.2% water. The balance, 94.8% inert. Okay, so how do we operate this? Remember, we are still on the overall boundary, but again, we cannot use our normal OMB. So let's first consider the tie components. What is your first tie component if you take a look at the bottom streams? The tie component here is rise, because water enters at F and S and exits at P and W, so we cannot use the water balance yet. Let's perform the rise balance. We have 0.75 of F is equal to 0.95 of P. And P is, as our basis implied, P is 100. So we can directly solve for the value of F. 0.95 times 100 divided by 0.75. 126.67 pounds. You have to be careful between pounds and pound moles. So we now know F, we now know P. How do we determine S and W? We cannot use water balance because water balance would give us mixed results because there are pounds and there are pound moles. So let's take a look at another tie component. This case, the tie component from the upper streams is the inert because the inert only enters in S and only leaves at W. So it's also worth noting that our rise balance has units of pounds because we are talking of F and P, while our inert balance would have units of pound moles because we are now talking of the S and the W. What is your inert balance? That's 0.9527 times S equals 0.9069 times W. Equation number 2. So that is our inert balance containing two unknowns. Okay, now how do we determine another equation to solve simultaneously with equation number 2 so that we can get the values of S and W? We now go to the water balance. However, as I have mentioned earlier, for your water balance, we cannot simply have this as water in F plus water in S equals water in W plus water in P. Because the water in F and in P are in pounds, the water in S and in W are in pound moles. So we have to reconcile the two. So what I will do here is I would simply just rearrange the equation and represent them in another way. The water balance is simply the water in S plus the water absorbed. This should be equal to the water in W. Let's examine this equation. So common sense dictates that if we take the water that is incoming from S and if we add the water that's being lost by the rise, so remember, you are drying the rice, therefore water is leaving the rice and is joining the gas stream. No? So that is the water absorbed term here. The water absorbed or the water lost by the rice in this process is simply calculated as the water that was initially present in F minus the remaining water in P. Now, this might look very confusing, but if you perform the conventional water balance, this is simply water in F, which is the input, plus water in S, another input, is equal to the water in W plus the water in P. If you take the water in P, transpose that to the other side of the equation, we would have this one, water in F minus water in P. That is simply the amount of water absorbed. Okay? So let's first calculate how much water was absorbed. So the amount of water absorbed is equal to the water in F, that is 0.25 times F, 126.67, minus the water in P, 5% of 100. So let's calculate how much water was absorbed. 0.25 times 126.67 minus 100 times 0.05. 26.67. Unit, this is pounds of water absorbed. Now, in order for us to use this value in our water balance, we have to convert this to pound moles, because remember, S and W are represented in pound moles. So let's convert this to pound moles. Molecular weight of water, 18 pounds is to 1 pound mole. Divided by 18, 1.482 pound moles water. Now we know that there is 1.482 pound moles of water that was lost from the rice and was absorbed by the air in the drying process. We can now substitute this to your water balance. So let me first erase some things. So what is now our new water balance? The water in S is 0.0473 times S plus water absorbed, as we have determined earlier, is 1.482 is equal to the water in W, 0.0931 W. We now have our third equation. And we were able to obtain the third equation by playing around the given, because we cannot directly solve for the water balance if there's a mix between pounds and pound moles in the unit. So equation number 2 and 3 are both now in pound moles. We can now solve them simultaneously. Let's let S as X and W as Y. The coefficients are 0.9527, negative 0.9069, and 0. Second equation, 0.0473, negative 0.0931. The constant is negative 1.482. We have a value of S as 29.35 pound moles per, just pound moles. And then W is 30.83 pound moles. Now you can pause for a moment and think if the values of S and W make sense. So the value of S, 29.35 pound moles, that is the amount of stacked gas entering the process. Remember, the purpose of the gas is to absorb the water so that you can dry the rice. The gas exits heavier than before. That means that the difference between S and W should be the amount of water that was absorbed. So let's try. If you subtract S from W, what do we have? 30.83 minus 29.35. The answer is 1.48, which was the amount of water that was absorbed. So we know that we are correct. 1.48 pound moles water absorbed. Okay? So now that we have the values of S and W, we can now go back to determining the value of R. Remember, the required here is the value of R. Ask yourself, what balance or what boundary can we then take so that we can get the value of R? You have several options. You can perform the balance on the dryer itself. So you set the boundary on the dryer. We can also set the boundary either at the splitting point or the mixing point. Where do we have most of the given? I think we need to perform the balance at the mixing point. That's because we know the composition of M, or we know the composition of the mixed feed, so we can get the value of R. So let's try. I have copied the values of S and W for our reference. Let's try to perform the balance at the mixing point. What is your OMB? Input S, another input R is equal to output M. For us to get the value of M, we need to know the value of S and R. We already know the value of S, that's 29.35 pound moles. We don't know the value of R yet. So we substitute 29.35 is equal to 29.35 plus R is equal to M. That is our equation 4. I think we are already at equation 4. Component balance. The component that we are familiar of in this case is water. So let's perform the water balance at the mixing point only. So what's your water balance? 0.0473 times S plus R. Now the question is, what is the composition of R, or what is the water content of R? Now take a look at the splitting point here. Remember, this is a splitting point, and if you would recall, splitting points always have the same compositions for their inputs and their outputs. One of the output for the splitting point is W, which contains 9.31% water. That would mean that the recycled stream should also contain 9.31% water. This is a vital information that was not mentioned in the problem that you should know so that you can solve this problem. Going back to the water balance, we have 0.0931 times R is equal to M, 0.052 M, equation 5. We can now solve equations 4 and 5 simultaneously. So let's use R as X and M as Y. So for equation 4, the coefficients are 1, negative 1, negative 29.35. For equation 5, first coefficient is 0.0931. Coefficient of Y is negative 0.052. And then the constant is negative 0.0473 times 29.35. We now have the values for R. R is 3.36 pound moles, and M is 32.71 pound moles. So we are interested with the value of R, 3 significant figures, so this is it. 3.36 pound moles. Of course, with the required, we want to determine the amount of pound moles of R per 100 pounds of P. But we have already set our basis as 100 pounds of P, therefore, this is our answer. So we need 3.36 pound moles of R, or pound moles of recycles, per 100 pounds of the product, which is dried rice. Okay, so just a reminder, as illustrated in this problem, you have to carefully decide whether, or you have to carefully discern whether you have a mixture of units or whether you have homogeneous units. So carefully check the problem before you solve it. In this case, we have a mixture of mass and mole units which cannot go together. Okay, next. £10,000 per hour of a 40% sodium hydroxide solution is crystallized through a combined evaporator crystallizer process. Okay, so this is the same as our example number 1. So this would be your number 1 for worksheet number 5, if I'm not mistaken. Okay, I will be giving the other numbers for worksheet number 4 and worksheet number 5 in Blackboard later. Okay, so please take note that this is number 1 for worksheet number 5. Please watch out for the next items that I will be uploading. I plan to upload some more examples for multiple units and for recycle, bypass, and purge with solved solutions so that you can have a reference for more examples. Okay? Also, please watch out for the additional items for worksheet number 4 and worksheet number 5. So this is the end of this lecture. I hope you have learned something. And as always, keep safe.